Okay. In the interest of time, I'll try to cover as much topics as possible in the storage topic in this lecture. A lot of the topics here are just loose, very high-level introduction to various topics and technologies and things like that. So it's more like a museum of ideas more than anything. Okay, so let's get started with the first tidbit. So last lecture, we talked about the some of the technologies enabling high performance storage and some caveats of what some of those technologies have, the caveats that they have. And this lecture, we're going to talk a little bit about from the perspective of, say, a system engineer, perspective of a software engineer, how can we actually make the best use of these kind of storage? Or because the very fact that I have a slide titled something like this means that if we just use it the way that we used to, like at least at the introductory level of computer science, if, for example, if you use fopen and fread and stuff like that, that's possibly not enough. That's the whole reason that I'm talking about this topic. So let's get into it. Before we get to the actual programming models that we as programmers need to deal with, there's a little topic on the topic of flash optimized file systems. We all use various types of file systems on our daily machines. If you use a Linux machines, it's likely that you'll be using ext3 or ext4 file systems. If you use Windows, you're most likely going to be using exFAT. If you're using an older version of Windows, or if you're using a USB thumb drive, you might be using FAT32 and things like that. There's various different types of file systems, and the generic file systems that we use on our day-to-day lives are typically optimized for spinning magnetic disks. Well, and the slow speed and the slow random access performance that these things represent. And we talked about how the characteristics and performance features of flash storage are very different compared to, and of course, how to use it well differs a little bit at least from how to use spinning magnetic disks. So there's a whole topic on doing research for file systems that are optimized for flash characteristics. And the big MO of this subtopic is that it tries to organize I/O to make it more efficient for flash storage, and the fact that it has an underlying FTL. And typically, flash optimized file systems come in the form of the so-called log structured file systems. And this comes into play because, as we talked about in the last lecture, flash storage and most SSDs in general do very badly with random in-place updates. So FTLs, we already talked about how if we try to do FTLs, try to have a circular write log and tries to have a pre-erased pool of pages so that random page updates can be applied directly in a sequence. And similarly to that, to take advantage of the high-level information that file systems might have, as opposed at a higher level than the FTL at the device level, flash optimized file systems tries to do something like when there are random write requests come into the file system, they may be from the perspective of the file system, the updates might not be at page granularity. You might be sending fwrite to 28 bits somewhere, for example. And these kind of random writes, instead of being applied directly to the file system, say by doing a page read, modify, and then a page write, these random writes are first written to a circular log in host memory inside the file system. And then only when the write units become kind of big, they're applied all at once. So that hopefully we can have a lot of, we can collect a lot of writes going to the same location, for example, or collect a lot of write requests in bulk so that we can get higher performance at the benefit of scale. Oftentimes, there are multiple logs involved in flash optimized file systems, involving things like hot and cold data, different queues for hot and cold data. And when read requests are sent to pages or pieces of data that has not yet been applied to the storage yet, they're still sitting in the queue, then the file system will scan the in-memory queue to return the data without actually having to access the storage. And because the data that is currently sitting in a queue in a nice sequential fashion, because a queue is a single block of memory in memory, uh, if all of that data had already been applied to the backing storage, accessing that would have been very bad for disk. Yeah, because it would involve a lot of random access. And there's a lot of different examples of flash optimized file systems that are used here and there. I think some of the most prominent examples are phones use flash optimized file systems quite often. Sometimes they're also used in data centers, etc. I think F2FS was one of the very first, and ever since we have things like yet another flash file system and so on and so on. And if you look at the performance that flash file systems do achieve, we're comparing other generic file systems like ext4 and XFS and F8 and FAT against flash file systems like F2FS and ILFS. And if you look at the direct read performance, where we're not using the OS cache, and we'll talk about how what OS caches, file system page caches are. When we do reads, regardless of whether we do random reads at large granularities or sequential reads at large granularities, random reads at small granularities and sequential reads at small granularities, the performance, there's not much performance differential between flash optimized file systems and regular file systems. This comes from the benefit of flash storage itself, because random reads are pretty good in terms of performance pretty much always. The reason random small and sequential small are unanimously slower than sequential large and random large is because of the access granularity mismatch we talked about in the previous lecture. If you have to read a 4 kilobyte page and only use 8 bytes of it, then of course performance will go down. More interesting results come in when we look at the direct write performance. So we're not using in-memory buffers for writes. Again, for all write requests, we're sending it directly to storage. And when we do have something like that, there is a pretty significant performance difference between these two bars, the flash optimized file systems compared to the regular file systems. Same for random small and sequential small. And this is because when we do write requests, the fact that we can buffer a lot of potentially random, of course, if we go sequential access requests, they're not random. But the fact that we can buffer a lot of write requests and then send them out in chunks do have very, very good performance characteristics. And performance differentials get even better once we go to buffered write, where the OS buffer is allowed, the OS cache buffer is allowed to actually absorb some of the writes that may be cached inside main memory, for example. And in these kind of examples, in these kind of situations, even for very small write requests, random small and sequential small write requests, the flash file system performance is typically superior compared to just regular file systems, thanks to the better affinity between the file system software and how it functions and the underlying storage hardware. Well, the takeaway from all of this is it's not necessary to try to comprehend what all of these different bars mean. The takeaway from all of this is that flash file systems are typically optimized to improve the write performance on NAND flash-based storage devices. And it does show. For random access, everyone works pretty well, but as the workload becomes write intensive, there is a pretty significant performance differential between flash optimized file systems and regular ones like ext4. So that's one topic. The next tidbit of topic is the issue of queue depth and its relation to performance. So remember, performance improvements in flash-based SSDs came from the fact, well, some of it came from the fact that there's many chips organized into many buses. And inside buses, there's also multiple chips that can be functioning in parallel. But that performance, that parallelism can only be extracted if you have multiple read or write requests that are being sent out at any given time. For example, it wouldn't matter if you have 8 buses. If you're waiting for a previous request sent to a particular bus, if you're waiting for that request to come back before you send out the next request for whatever reason, it could be that the next request depends on the value that you're going to read. If you do something like that, then your queue depth would be 1. You only have 1 request in flight at any given time. And the parallelism that is available from across buses, across different chips on the bus, all of that would not be usable. So in order to get high bandwidth, enough requests must be in flight to keep all the chips and buses busy. And if you're using, for example, fread, read, mmap, these kinds of regular functionality that you're used to, for example, if you send fread is a blocking function call, if you remember. So this function call will not return until the data is actually finished being copied to the user space buffer that you gave it. So this matters less if your read granularity is high. If your fread is always being called at, say, 4 megabyte granularities, then that would represent many 1,004 kilobyte pages being read. Request for 1,000 pages being read would be sent out as a result of that one function call. If something like that happens, the underlying operating system, file system, all these guys can actually translate this one function call to 1,000 read requests being sent out to make good use of the queue depth. But if your application is random access intensive and you're using fread to send out very small read requests, 4 kilobyte read requests, 128 byte read requests, or something like that, then every time you call fread, you will be using the underlying storage at a queue depth of 1. And that would be very bad for performance because between the time you call fread and until that fread function call actually returns, that underlying storage system is only being used regardless of how many chips, how many buses are installed on your storage device or storage system. If you're between the time you call fread and fread returns, only a single chip in that whole infrastructure is being busy at a given time. And the performance difference is pretty stark if you look at this chart. The lower bars here are from SSD, NAND flash-based SSD storage devices. And the blue bar here is from the Intel Optane, so the cross-point-based storage class, not storage class memory, because this thing actually plugs into the PCIe. So Optane-based, cross-point-based storage device. This is a NAND flash-based storage device. Optane has a much lower access latency compared to NAND flash. So the performance improves to its peak levels at a relatively low queue depth, say 4. But if you're using off-the-shelf NAND flash SSDs like the PCIe SSDs or SATA SSDs, then your queue depth needs to be 32, 64, or even higher to actually get the performance that these devices can get you to reach that peak performance. For example, if you're using a PCIe Gen 3x4 M.2, which seems to be the norm nowadays, to get the 3.6 gigabytes per second that the device promises, then you need to always have 64 requests being serviced by the storage device at any given time. If you have 2 storage devices plugged in, then 128 request needs to be in flight issued at any given time to actually achieve this peak performance. And there are multiple different ways to actually achieve this. The simplest would be to send out read requests at coarse granularities. If you're sending out fread at 4 megabytes in size or more, even a megabytes order is typically good enough, I've experienced. But if your application doesn't allow it, if your application requires lots of random access from a very, very large data set that's sitting in storage, then just this single-threaded fread sequence is not enough to actually get the good performance. You'll be sitting around here, multiple orders of magnitude performance lower than what you could have achieved if you were able to somehow provide a very large queue depth. And there's in that kind of a situation, there's multiple different ways to approach the problem. One of the more traditional ways to address this was using a thread pool. So you would, at the beginning of the world, when your program first starts, you would use pthreads or something to create, say, 64 threads. That's a lot of threads, but if, say, 64 threads, and all of these guys will be doing is, if you send out a read request, one of the threads will be tasked with the task of executing fread, and when it's done, it returns the value the read values to the home thread. And hopefully, at most of the times, these 64 threads, all of them will be busy waiting for storage to come back as a result of fread. And when these threads are busy waiting for storage, then they will be the thread will be yielded. It would not actually be consuming chip space, not be consuming CPU time. So even though you would have 64 threads running for your application, it wouldn't actually represent 64 core times worth of, CPU wouldn't be as busy as you as executing 64 compute-intensive threads. Most of the threads will just be sitting there waiting for storage to come back. So that's one way to do it. And there's actually a library, well, many libraries, but a couple of libraries that actually provide this functionality. For example, the POSIX AIO library, POSIX asynchronous IO, and we'll talk about this in a bit. And there's many others. And you can use these libraries when you start it. It will spawn a bunch of threads. If you send out a lot of read requests, then it will spawn some more threads. And these threads will be used to perform the blocking read and write storage requests so that you can have a very large queue depth. And when the requests are serviced, then it will send a message or something to the home thread saying your request is ready. So, and the home thread can be doing something else in the meantime. So that's one way to do it. And we'll talk about some of the details of this in a bit. But now to move on to the next, before we move on to the next topic, some backgrounds. We talked about page caches already in a couple of slides back. Page caches. Linux and most other operating systems as well, including Windows, keeps the so-called page cache in the kernel that stores some pages, some storage pages previously read from storage, buffered inside memory. Kind of like CPU caches buffering accesses into off-chip memory, the in-memory page caches managed by the kernel does the same for the storage devices. And at least in the case for Linux, it automatically tries to expand into unused memory space. If you have a lot of system memory that is, well, not even a lot, if you have a little bit of system memory that is not being used explicitly by some application, the kernel will expand the page cache into that unused memory space so that memory would not be sitting there unused. And if you're writing a very performance-sensitive application, sometimes it makes sense to try to stop the kernel from doing this because it does result in some memory IO requests being sent to the main memory that you might want to actually explicitly use for other reasons. But in most cases, this works fairly well. If you have multiple gigabytes of memory not being used at any given time, your storage previous storage accesses are, instead of being applied right back into storage, it's buffered somewhere in main memory. And when you send a memory read request to a location that you've already accessed before, then that read request will be serviced from memory instead of having to bother the storage, having to bother the slow storage. So if you have a page cache hit, it results in pretty high performance, of course, because you're not accessing storage, you're accessing the much faster DRAM. And however, this does mean that if you read data from storage, it involves multiple iterations of copies being made. The data has to be moved from the device to the kernel where the page cache is. And then from there, it has to be mem-copied again to the user space where the actual destination buffer that you gave to fread, for example, is located. And this is a simplified view. In a lot of file system implementations, there's more instances of data copies being made here and there through the process. And that's, in some cases, that is actually a pretty significant performance overhead. That's some of the things that, say, flash optimized file systems tries to do away with. And if you want to actually look at the impact of page caches, you can go into sudo and then write 3 to this particular file to flush all of page caches. And then once you do that, if you try to read a big file again, you will notice that the storage becomes noticeably busy and the performance might be kind of bad for a little while. If you're doing some research on storage performance or performance analysis of systems that have storage, and you want to get rid of page cache artifacts in performance, because if something has been cached already from running a previous experiment and you want to reset the system into a known state before you actually run the next experiments, this is what you can do. From the software level, if you want to bypass the page cache and hence bypassing this multiple copying issue and things like that, you can use what is called the direct mode. And when you use the open syscall, you can give it the flag odirect, and it will return a file descriptor with the file open in direct mode. In direct mode, there is much lower operating system overhead. So typically, if you know what you're doing, you can get better performance, like noticeably better performance. But it does have no benefit of page cache hits because we are bypassing the kernel, most of the kernel, and we're bypassing the page cache. So without odirect, if you had written to a particular location in the file and then you try to read from that location again later, you may have hit the page cache, getting you better performance. But if you use odirect, then page caches aren't managed for this particular file, and you wouldn't get that benefit. So there's some decisions you might need to make. This is very useful if the application performs its own caching, or if it knows that there is zero reuse. For example, if you are writing a database, then odirect would probably be absolutely necessary because the database knows best on what to cache and not. Or if you do something like graph analytics, where the data size is so large and the access patterns are so random, the potential benefits of reuse by the page cache is very low, then you might want to go with the odirect approach. So that's some background on page caches. And with that in mind, let's go a little bit deeper into asynchronous I/O. So remember, because we want to have a very large queue depth to get performance, we want to have many in-flight requests created. And asynchronous I/O allows to do it by sending out requests in a non-blocking manner, which allows you to create a lot of I/O requests from a single thread. So for example, if you look at the synchronous example of doing file I/O, say if you use fread, you would call fread at this point. The read request is sent to the storage, and the response comes back from the fread. And at this point, the software returns from the fread system library call. And then only then you can send out the next request. And this is fine if the requests are large enough. But if the requests are very small, then the CPU isn't doing much while it's waiting for the data to come back. The storage isn't doing anything much between the time it's sent out the response and then waiting for the next request to come in. Not to mention, like I said before, at least for SSDs, parallelism comes a lot from having multiple buses and multiple chips per bus. If the read requests are very small, even when the device is busy, quote unquote busy, only one chip would be busy at any given time, dropping a lot of performance on the table. And here's an example with asynchronous I/O, with a queue depth of, say, larger than 7. And because the file I/O requests are non-blocking, the software can just keep moving forward, sending out more requests, without acknowledging or waiting for the responses to come back from storage. And it can handle the responses when it comes back in an asynchronous manner, only when the results are ready. So this way, even though we only have one thread on the host, it is possible to send out pretty much fill the necessary queue depth to get the maximum performance out of your storage device. And it seems at least the rule of thumb, the anecdotal experience right now is that, well, let's talk about that in the next lecture, because next lecture we're going to talk about actual software. There's a couple different ways to do asynchronous I/O, and there are more options beyond this. This is just some of the more prominent ones that I wanted to talk about. The first option is using the POSIX AIO library. I alluded to this in one of the previous slides, and this is a user space library that you can just import like you would import at pthreads. And from the POSIX AIO library, libaio, libaio is the kernel one, the POSIX AIO library, I won't go into too much details about this because details are abundantly available at other places like Stack Overflow. I just want to touch on as many points as possible at this lecture. But anyways, what POSIX AIO does is that it creates a pool of threads to offload blocking IO operations. Each thread will be working on a blocking IO operation. And because we have many threads, we can have many blocking IO operations working in parallel, which is how we reach queue depth. And here the queue depth is limited by the thread count that you can spawn, which is not a pretty severe limitation because you can spawn as many threads as you want, hundreds, thousands of them, as long as they're not actively busy waiting or anything. If they're all waiting for a synchronous IO to come back, then they'd be not scheduled by the CPU, which is fine. And the POSIX AIO libraries is part of libc, where the standard IO and all that stuff is. So it's very easily portable. And it does work with page caches because under the hood, it is doing something like fread pretty much. Another option is using the Linux kernel AIO library or libaio. You can compile it with the libaio flag. You can compile it with your program. And here, the asynchronicity management is offloaded to the kernel. It is not dependent on any thread pool or anything. The read requests and the responses and the asynchronous nature of that is handled by the kernel. It's under the hood. So you don't have to spawn too many threads. You just send up, kind of like using a system call. If you just send read requests, write requests to the kernel will let you know later when the responses are ready. So that's efficient and fast. One downside of AIO is that despite some efforts by the developers, it does not support taking advantage of the page cache yet. So if you want to use libaio on a file, you have to open it using odirect. And like before, this approach is especially good for applications that manage their own caches like databases because it is fast, but you have to use odirect. Another option that is relatively recently became available is a set of system calls called the kernel uring. I won't talk too much about the uring yet, but it is a relatively new thing which pretty much seems to do everything that the libaio library does, but it also supports non-odirect methods. So it does support taking advantage of the page cache. So it seems to be the best of the both worlds kind of a situation. And from anecdotal experience using libaio, at least, if you have a 1 or 2 PCI attached SSDs, Gen 3x4, 4 to 8 gigabytes, that kind of a level of throughput. If you use libaio, you can get maximum throughput. You can get maximum reads from just one thread. So but it's really pushing it. If you install more storage devices, you probably would start to need more immediately. But with 1 or 2, one thread seems to be kind of enough. It's a different story whether you can actually do the processing that you want to do on that many pages being read per second, because actually doing the computation becomes a much more severe bottleneck at that point, especially at multiple gigabytes per second throughput. You may quickly notice that even if you're doing something very simple, like you would read a page and then just count the number of odd numbers there, for example, that's a very, very simple application. Just scanning over the 4 kilobyte pages, looking at 4-byte numbers, seeing if each value is odd or even numbers, for example. Even with an example as simple as that, it is likely that a single thread implementation will not be able to keep up with a single PCI attached storage device. So the way you think and manage storage will typically has to change a little bit. And I'll just do a very short introduction to libAIO, just to put this in the back of your head in case you want to use it later. The basic flow of using the kernel libAIO is to first, kind of like how you would use pthreads, you first have to create a context using the IO setup function. And then every time you want to send a storage request, be it read or write or whatever, you create a struct IOCB for each request, and then submit it to the libAIO framework using IO submit. And later, you can poll or periodically check if any of the requests you previously sent has been completed by using IO get events. And you don't have to always use one AIO context for everything. You can create multiple AIO contexts from if you want to have multiple different queues, semantically different queues. Yeah, and if you want absolutely the best performance, you might want to create multiple contexts across different threads with a large number of, so NR events here on top is the queue depth. So large NR events, 100, 200 or more across multiple threads. That would be the absolute best performance. But you do need to, if you really have to make this choice, you do need to probably benchmark your system a little bit using various different configurations to see how many threads you actually have to assign to this to get the best performance, because you would need threads to do actual work as well. Yes, yeah, and multi-thread, like I was just saying, multi-threading is probably necessary not because of AIO overhead. Typically, if you have a 1 or 2 PCI storage SSDs, a single thread of kernel libAIO is probably enough to keep the storage busy. But to actually process the data that is being piped in at multiple gigabytes per second, you probably do need to have multiple threads. So just to give a very short example of how this actually would work, you would have this when the slides are uploaded. You can hopefully when you use it, you know where to look. You can do IO setup with the IO depth for the context. And then for every single read or write request, you can call, say, there's a helper function called IO prep for write. And you give it the IOCB data structure pointer, which file, the buffer, how many bytes, from which offset, et cetera, and you can do IO submit to submit this request to the AIO system. And periodically, you can call IO get events to return how many events have been completed and which of the requests have been completed. So you can look at which of the requests has been completed, how many of the requests has been completed. So you're looping over the done requests. And for each request that's completed, you can get for example, the pointers for the original IOCB request, which will include, say, the pointer to the buffer that you wanted to read a piece of data from, for example. Yes, and like I mentioned, even with 8 kilobyte random accesses, a single thread can saturate at least one multi-gigabytes per second NVMe from just anecdotal experience, which is very, very efficient. It's much better than having to spawn 64 threads to create a thread pool. So this is the asynchronous storage access approach, and specifically kernel-based approaches. There are different approaches as well, for example, user space IO libraries, because even for libAIO and people like that, syscall and these kernel user data copying does become relatively expensive as storage performance becomes faster. If you look at the breakdown of performance across different storage technologies on the right here, the y-axis is the percentage. It's not the absolute performance of these storage devices. It's the percentage breakdown of performance overhead. So on the leftmost side here, we have a relatively slow HDD, 7K RPM HDD. You have things like SATA SSDs, NVMe NAND SSDs, and then Optane, and then regular old memory, not regular old memory, cross points to obtain memory. And if you look at because y-axis is kind of the latency, if you had plotted the absolute latency of all of these storage devices, the chart will look kind of like this. Exponentially faster, exponentially lower band latency with as we move towards the right. But here we're only looking at the percentage breakdown of latency. So they're all normalized to the same height. But anyways, the blue line, the blue bar is the latency of the actual storage device. And the orange bar is the latency of the software involved in reading the data, reading or writing the data. Reading the data, because it's drive read latency. So for HDDs, just because they're just so slow, the overhead of software is pretty negligible. Software can do whatever it wants, do as much complex computation it wants to send out before sending out read requests, but compared to the millisecond latency potentially of storage reads, then this is software overhead is negligible. But as performance becomes faster and faster, the software overhead becomes more and more prominent sources of performance degradation. And a big part of that is copying data, copying data to the kernel, copying data back from the kernel, doing a kernel system call, getting an interrupt back from the storage, and then the interrupt rescheduling the original thread, things like that. All these kernel level work is a very high performance overhead people have discovered. So there's a class of user level IO libraries which tries to bypass all of this so that we can do things like just busy wait if you know that the results are going to come back pretty soon, and not having to copy data to the kernel, things like that. And so one of the more prominent examples of this is the Intel SPDK, Storage Performance Development Kit. It is a user space library, no locks, interrupt free, because we haven't talked about interrupts very much in this lecture yet, but interrupts are pretty expensive if you are very latency sensitive, because for example, when the storage data copy is done, data read is done, and the storage sends an interrupt to the host machine saying, "Oh, I'm done." The interrupt handler will be called inside the kernel. The interrupt handler will reschedule the thread that needs to be returned from the storage read functional call, for example. And this rescheduling latency is in the orders of microseconds to milliseconds. So if you're talking about storage devices with access latencies in the orders of microseconds, lower end of the microseconds, this polling overhead is fairly significant. So instead of interrupts, many user space IO libraries just implement busy waiting, just polling, just spinning in a while loop until everything is done. And that typically gives you much, much better performance. So there's that. So this has been the underlying storage infrastructure, underlying storage management software topic of things. We're going to just spend a little bit of time talking about some data structures for storage, which might benefit you if you try to write software which tries to make good use of fast storage. And we'll hopefully by the end of the lecture, I'll get to talk a little bit about some of my previous research on actually doing this efficiently, achieving really high performance at orders of magnitude lower cost and power consumption. Anyways, so there's a wide class of algorithms and data structures that are optimized for storage use. Typically, these are called either external algorithms or data structures, or out-of-core algorithms and data structures. Both of these terms typically mean storage. And the common theme in these algorithms and data structures is that they force coarse granularity of access. Instead of just being oblivious to the underlying memory, as you would, for example, if you write a textbook binary search tree, you would not think about the underlying granularity of storage or memory access. You would just assume if you send out if you access an array, 4-byte array, then you get the 4-byte data back. You won't care about those underlying storage characteristics or memory characteristics, but these algorithms, kind of like the cache oblivious algorithms that we talked about, and I just want to point out all of those algorithms can be directly applied here as well. But coarse granularity of access into the underlying memory or storage. And also they prioritize sequential accesses, especially if the access granularity is fine. Yes, and most of what we learned about the cache oblivious data structures also work here, including, for example, the use of B-tree. We talked about the B-tree as a potentially easy way to get high performance, even compared to the cache oblivious Venom the Boas tree layout we talked about before. So this is the same chart I showed for the cache oblivious topic. The y-axis is elapsed time in logarithmic scale, exponential scale. The topmost line is binary tree, and the two bars below are the cache oblivious Venom the Boas and a B tree with 1024 elements per block, per node. And yes, anyways, B tree is a generalization of a binary search tree where each node can have more than 2 children. The binary search tree is binary because each node can have 2 children, but B tree is generalized so that it can have more than 2 children. For example, in this example, it has 1024 children. And typically when you use a B tree for storage, and this is in many cases at a very high level what databases do, is typically you put enough children in each node to fill a file system page, a 4 kilobyte page, so that the data that you load from storage is not wasted, so that all of the data, all of the 4 kilobytes that you read is used for something. If the page size is known, if you know that the page size, the underlying page size of the flash storage or the underlying page size of the, say, disk is known as 4 kilobytes or something like that, it is a very, very effective data structure. Even compared to the very complex and very optimized Venom the Boas tree layout, when we know, armed with the knowledge of the page size, the fact that the page size is 4 kilobytes, so it can fit 1024 children into it, the performance is very, very good. Of course, if the page size does not match our assumptions, then there would be some performance noise, but it's a very good approach to take, especially since Venom the Boas trees are just fairly annoying to actually get right. Right. To go just a little bit more into the B tree as a quick recap, the B tree is a self-balancing structure. That's one of the reasons it's so efficient. When all you're doing is insertion, for example, insertion is always done at a leaf. You first traverse the tree to discover the place where we would need to insert it. For example, if you want to insert a value 8, for example, you compare between 7 and 16. So you go to the middle leaf, and then you compare against 8 and 12, so that you know that I can now insert it in before 9. In that kind of way. Insertion is always done at the leaf. And the special case is that if the leaf is full and you can't insert it into that leaf, then the leaf is split. The leaf is split, turning it into 2 leaves, which would mean another value needs to be inserted into the parent to accommodate for the new leaf that's created, to act as a divisor. And if the leaf splitting results in an overflow from the parent as well, for example, if the parent was already full, then the parent is split, and we keep repeating that upwards until the splitting is, correctly serviced, or if the root node is split as well. If the root overflows, then we create a new root and then split the old root. So by doing this, the tree height always increases from the root, automatically keeping the tree kind of balanced. So it's a very efficient data structure because the height of the tree, if the depth of the tree starting from the root to any direction, in any direction, is kind of in a similar order of, or kind of a similar depth. So yeah. So the number of nodes that you have to traverse is always kept very low because the tree is balanced. Things become a little bit more complicated when you have to do deletions, because if you delete from a node and it causes an underflow, if a node disappears, for example, if all of that happens in a very bad way, the tree can become unbalanced. So there are special cases, and you have to rotate some values in some of these nodes. You have to move some values from the leaf to the host, some values from the leaf to the parent, some of the values from the parent to a different node, doing rotations in that way to keep the tree balanced. Yeah, rotations in the case of node underflow, but we won't go into too much details about that right now in the interest of time. I just want to use that as a segue into introducing the B plus tree in case some of you are not aware of it. So B trees were efficient when the values that you deal with are just scalar values. You deal with the value 4, for example. You deal with the value 7, things like that. B plus trees are B trees which are modified to efficiently deal with key value pairs. So the values that we're using to insert and query the trees and all that stuff would be keys, and attached to each key, we will have a value that is completely different from the key types. For example, if you're thinking about databases, well, a key value storage is pretty much a database in and of itself, according to some definitions. But say you can have a index of URLs which point to a image, for example. And in that case, you can have a database of URLs pointing to a binary representation of an image. In that case, the keys would be the URLs, the values would be the images. So when you want to query for a particular image, you would traverse the table looking for that particular URL, and it would return the image when it actually finds it. So that's a key value pair. And B plus trees are B trees modified to effectively deal with key value pairs. Compared to the B tree, where all the nodes were just the same nodes in different locations, in B plus trees, there are explicitly two separate types of nodes: internal and leaf nodes, internal nodes and leaf nodes. Right, B trees had elements in both intermediate elements that we inserted and deleted and referenced. All these elements existed in both intermediate nodes and leaves. But for B plus trees, internal nodes only contain keys for keeping track of the children, and values are only stored in the leaf nodes. And all the leaves in the bottommost layer are also connected to each other, one after another, in a linked list. So here's a pointer in the red box pointing to the next leaf. Here's a pointer in the red box pointing to the next leaf, so on and so on. And this is very efficient for when you're dealing with key value storage and things like that, because you can do efficient range querying. You might want to say query for all key value pairs between the key values of 7 and 24, for example. If you didn't have this linked list, you'll have to traverse the tree for every single value in between, or at least start from the key value 4 and then go to the right, and then traverse back up, and then go to the next list, and then go to the right, and traverse to the host, traverse to the parent, and then go down, etc., etc. But if you have a linked list, you just traverse the linked list, starting from the leftmost to the rightmost, until you reach the key the end of your predicate key. So it's very efficient for range querying. And this still works very well with storage, because just like B trees, these intermediate nodes and the leaf nodes are large enough to make efficient use of the file system page sizes. So that's trees. Another tree that is was very popular for working with storage devices, especially flash storage devices, is a tree called the lock structured merge tree. In many cases, it seems that if you want to have a data structure which supports random writes and even random reads, and you want to host that inside a storage device, the rule of thumb seems to be just go to an LSM tree. It works very, very well. So it's a tree structure that is storage optimized, and it is a key component of many modern DBMSs, including RocksDB, Bigtable, Cassandra, and all these people. It's very, very widely used. And the LSM tree consists of multiple in-memory data structures and multiple immutable, so they can't be updated once they're created, immutable external and storage data structures. So if you have a tree LSM tree and you want to send an update to a key that's already been inserted into this tree, then updates are applied to the in-memory data structure only. The in-storage data structure is not updated at all. And this in-memory data structure is regularly flushed to create a new instance, to create a new immutable data structure in storage. And we're going to go into a little bit of details about what these things actually are in a bit. And when you do lookups, lookups must first search the in-memory structure and potentially all instances that exist on the storage in the storage, if not. So, okay, that may have been a little bit a woozy introduction to all this. Let's go into a little bit of detail because this is an important data structure. Right, okay, just a figure. You can have a in-memory data structure and for a key value, for keeping track of key value pairs. This can be a regular dictionary, a tree, binary search tree, whatever that you think is good. And every time this tree becomes too big or it's been too long or according to some other criterion, this whole tree is flushed into the storage. And this tree is, this in-memory tree starts from new. So every time there's a read request query, you first check the memory in-memory data structure. If it's there, perfect, you return it, you're done. If you don't find it in memory, you don't know for sure that it doesn't exist in the whole data structure because it might have been flushed before into the in-storage data structure. So when that happens, you have to look at all of these, potentially all of this in-storage data structures in reverse chronological order, starting from the most recently created one to the most oldest one. If you find it in one of these files, then great, you return it. If you don't find it, you have to go to the next one because you don't know for sure that it doesn't exist in one of the older files. So I don't know, wait, right, yeah. You have to keep going and you have to potentially keep going. And that may, if you don't handle that well, this data structure may not have been very useful because of that performance overhead. Anyways, so yeah, because these external structures that is being flushed to storage are immutable and their numbers and sizes only ever increase, you have to do periodic compaction. You have to take some of the files, the older files, when the data structure is not too busy, you have to choose some of the older in-storage files and then merge them together. So that if you have value updates to the same key in the two file, for example, you only keep the newer one. If you have a deletion, you only keep the newer one, which means if you have a deletion request in one of the files, then the values inside the older files are removed, for example. But this still does constitute some performance overhead, although the efficient random access characteristics of the LSM tree offsets most of this to the point that it's still very, very efficient. And when you do compaction, since the external data structures are created in a sorted fashion, in many cases, the external data structures are in a data format of what is called sorted string tables. When it's flushed, it is flushed in a way that the key value pairs are all sorted according to the key. So when you do compaction, you can do very simple merge sort between these two files to create a one sorted files. And if there's key collisions between two files, then they're handled only by keeping new data. When you have sent out, when you have a delete request, delete request into the main in-memory structure, what it does is that it just marks, it creates an, if it doesn't exist in the in-memory structure, even if it does exist in the in-memory structure, it marks that key as deleted. And when you flush it into the storage, when you compact, if you discover a key that's marked as deleted, then all previous values for that key are just ignored. So that's how all this works. And we look at the performance. Yes, if you look at the performance comparisons between binary tree, B tree, the log structured merge tree, and then just regular old mmap. If the cache sizes, so the blue bar, the red bar, and the yellow bar are cache sizes, so in-memory buffer sizes. As B trees work fine when the in-memory buffer size is very high, because that means you can pretty much accommodate most of the data in memory, so performance is really good. But when the relative size of the in-memory cache becomes smaller as it becomes smaller and smaller, the data structure becomes more and more inefficient. As opposed to the log-structured merge tree, when the buffer size is very, very high, it doesn't really get you too much benefits because you do have that overhead of having to flush, you do have that overhead of having to potentially sequentially access a lot of the in-storage data structures. But even as the relative size of the memory becomes smaller and smaller, the data structure is well optimized for storage access itself so that the performance is kind of stable. So it is a very useful data structure to have in the back of your head in case you want to have high performance with storage devices. Okay, so that's the data structure stuff. Let us bugger on into let us bugger on into the topic of organizing storage devices inside systems and data centers. Let's keep doing until we run out of time for today. Most of you may be already aware of this, but just in case this is new for some people, I just want to point this out on the topic of RAID. RAID stands for Redundant Array of Independent Disks, which is a technology for managing multiple storage devices, typically inside a single machine or an array. So if you plug in multiple storage devices into a single machine, you can of course have it appear as different devices. You can have it appear as SDA, well, always does appear as SDA, SDB. You can create different directories, different folders for these storage devices, or you can use something like RAID to create merge all of them into a single entity, at least from the software point of view. Due to limitations of fault tolerance, which we'll talk about in a bit, typically RAID is applied to a single machine or a single array of machines. And there are different levels of the RAID configuration, going from RAID 0 to I think RAID 6. Right now, typically when people say they use RAID, they either mean RAID 0 or RAID 5. We'll go into what that is in a bit. RAID 0 has no fault tolerance. And that this, I guess, by reflection means that RAID 5 does have fault tolerance, and we'll go into what that is in a bit. RAID 0 has no fault tolerance if no fault tolerance, and blocks in a logical storage device, all the blocks that you want to write are striped, and they're round robin distributed across how many drives that you incorporated into RAID 0. You can create a RAID 0 array with 2 storage devices, 4 storage devices, 5 storage devices, 8 storage devices, whatever. They're all going to appear as a single RAID 0 storage device if you install it, right? And the data that is being read and written to this single logical RAID 0 storage device is going to be distributed round robin into these how many storage devices you have in the cluster. And RAID 0, of course, gives you the fastest performance because theoretically, if you have 2 storage devices distributed, then you will get 2x performance. If you have 4, 4x performance, so on and so on. However, because it does not have fault tolerance, if there's a drive failure, if any of these devices die, then all the data that's stored inside that particular drive that died is gone. It does result in data loss. So if you created a RAID array with 4 devices and you just randomly lose one of the storage devices because of physical impact or age or whatever, then you lose data, and you don't know. There's really no way of retrieving the data that's gone. So your volume becomes unreliable. So that's bad. But performance high is good. Size of the blocks that are being distributed, the granularity of block striping is configurable. And it is kind of similar in use case to the Linux Logical Volume Manager if you use it on your Linux machines. This is also an approach which lets you collect a bunch of physical storage devices and makes it available to you as a single logical storage device. It appears as if you have one storage device, even with the agglomerated performance and capacity. So this RAID 0 is a simple way of getting high performance with multiple storage devices. So it has its uses. The other popular RAID configuration is RAID 5. RAID 5, much like RAID 0, stripes blocks across available storage, but it also stores what is called a parity block. So here's an example. If you have a file consisting of 3 blocks, A1, A2, A3, and you have a RAID 5 configuration with 4 storage devices, you store A1, A2, A3 in different storage, storage 1, 2, 3, and you create a parity block, AP, for storage number 4. And AP is calculated by simply XORing A1, A2, and A3 values. And this parity block is very useful because if one disk dies, for example, storage 1 dies all of a sudden, and A1 is just lost, because XOR does not lose information, because the number of ones inside the truth table is always maintained. So we can, as long as we still have 3 blocks, we can recover A1 by XORing AP, A2, and A3. Same when if we had lost A2, we can retrieve A2 by using AP, A3, and A1 XORed with each other. So that's good. As long as there is only one storage failure at any given time, and we can replace it fast enough before the next one dies as well, then even when storage devices die, we won't have data loss. That's very good. 2 disk failures at the same time cannot be recovered, which is bad. But that's something that RAID 6 fixes, but it does also have higher performance overhead. So that's why RAID 5 is typically one of the popular ones, it seems. RAID 5 does have slower writes because every time you write something, you do have to calculate the parity block and then also write that parity block. So there is performance overhead of having the parity block. And also it has decreased effective capacity because for every 3 blocks that you write, you do have to write another parity block. So you are running on 3/4 of the peak available bandwidth. But the benefits of disk failure recovery is very, 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 very strong. So if you care about redundancy at all, this is something that you can do. Of course, if you have software level redundancy management, like if you're using Hadoop or if you're using Spark, things like that, all of this becomes less important. But if you are just treating this as just regular old storage and you do want redundancy for failure recovery, then this is a easy and efficient way to actually do this. What I've kind of glossed over with RAID 5 is the existence of the degraded mode. If there's a disk failure, for example, it enters the so-called degraded mode. If for all accesses targeted to the disk that has failed and not available, all requests to this storage has to be served by reading all others. So if you want to read A1 from the previous slides and storage device 1 died, then every time someone wants to read A1, you have to send 3 read requests to A2, A3, and then AP, and then XOR them together to get the correct data you want to return. So you're getting 1/3 performance, a 3x slower performance when you're in degraded mode. And so you don't want to be here for very long. So when the disk fails and someone raises an alert, if there's an email that went out or something like that, the failed disk must be replaced and it must be quote unquote rebuilt. And when the RAID rebuilding is going on, all other storage devices, so in the previous example, A2, A3, and storage device 2, 3, and 4 are all read from start to finish and parity calculated for each block. So you do the XOR, XOR, XOR for each block to recover the original data, all of the original data that used to be stored in storage device 1. And once that's done, you return to a normal state, not degraded mode, and you return to normal work as if storage failure never has happened. So that's very good. But if you have many disks organized into a RAID 5 format, for example, if you have 16 storage devices organized into RAID 5, and one of the storage devices die, and you have to read all 15 storage devices to rebuild storage 1, it will take quite a bit of performance to read all of those 15 storage devices beginning to end. So sometimes people do what is called declustering to create multiple parity domains. So pretty much when you do create, even if you are creating RAID 5 with 16 storage devices to expose a single logical volume, you can, under the hood, divide the 16 storage devices into 4 units of 4, for example, to create parity multiple, in this example, 4 parity domains. So that works well. And this has less to do with RAID 5, but in just general organization of the data center machines. Sometimes people install what is called a hot spare disk to the storage device. So the hot spare disk in normal times doesn't do anything. It is plugged in, it is powered on, doesn't do anything. It's no reads, no writes, no platter spinning, nothing. It just stays there, not being hurt. And as soon as a storage device fails, it has to be quick. It can be used by the software to quickly replace a failed device. And all this failure talk may be a little bit sound a little bit out of into the cloud right now, but to set the notion of scale a little bit, at least for spinning magnetic disks, the expected lifetime, according to the manufacturers of the storage disks, the expected lifetime of storage disks in the data center is typically around 3 to 5 years, which is pretty good. You buy a machine, you use it for 5 years, and typically your machine won't die. Your HDD won't die within those 5 years, even under constant use, as one would use inside data centers. But the issues, all of these issues come in when you have a very large cluster with many machines. If your storage expected lifetime is 3 years, and you have 1,000 machines, each with a storage device in your cluster, 1,000 machine cluster isn't even a particularly large one in the cloud scale, you will have one disk dying every day. So once you get to that kind of a scale, all of this management needs to be automated. People can't be just going around doing nothing but replacing hard disk drives and rebuilding, RAID 5 arrays every single day. So all of these needs to be somehow automated. That's where a lot of these technologies come in and are, important. Okay. A short talk on storage inside the network. Prepare for lightning rounds of very high level concepts, even higher level than the stuff we were talking about just now. First is the issue of network attached storage. Network attached storage is that we're going to build a server which is dedicated to serving files, kind of like a file server. The network attached storage exposes a file level abstraction. So it does really expose like a logical volume to all the clients that are connected to the network attached storage, or NAS. So NAS device can also own its own local RAID. It can install whatever file system it wants, etc., as long as it exposes a logical file level abstraction to the remote clients. And it can be accessed via the file system or the network protocol like the NFS, network file system. I know that for the UCI HPC cluster, they use the ZFS file system, which functions in a similar way, or FTP even. NAS works is a fixed functionality system. It uses, because all it does is serve files and data to the remote clients, it uses an embedded system typically with some accelerators optimized for NAS functionality to get high performance, low power consumption, all that good stuff. And yeah, they can have things like hardware accelerators for packet processing, etc., etc. Of course, regular Linux servers are also, and typically are also configured to act as NAS, and that works very well as well. And each NAS node is a separate entity. It's a single box. It could be a big box, it could be a small box, but it is a separate physical entities. So if you build a large storage cluster consisting of many NAS storage devices, you also do need additional management to get that working, seamlessly. The benefits of NAS storage, network attached storage, is it's very easy to scale and manage compared to direct attached storage. If you have 1,000 machines, each with a storage device plugged in, those things can die pretty much. Multiple devices die every day. Someone has to go and physically plug things in. When you have to scale, you have to, if you want to increase the total capacity of your cluster, if you have a cluster of direct attached storage, someone has to go and unplug and replug in all these new storage devices. If you only want to expand it by 1.5x, do you only improve the storage devices of half the machines in the cluster, so on? It becomes a little bit more complicated. But if you have a NAS-based storage infrastructure, you can just buy another NAS box, plug into an Ethernet port in your data center, and that's it. If you need more storage, you can plug in more drives into the NAS box. This is the NAS box. You have a bunch of storage devices plugged in. Typically, these things can have dozens, hundreds of storage devices plugged into the box. It has its own memory and CPU. It communicates with the other clients over Ethernet, so on and so on. A potential downside of DAS is that it's difficult to scale out of this centralized single node limit. If you have a NAS box, it is connected to the Ethernet over some Ethernet port. And this Ethernet link can be the bottleneck as well. If you're connected to the rest of the cluster over a 1 gigabit Ethernet, then the total bandwidth that you can get from all of these storage clients are going to be that 1 gigabit Ethernet bandwidth. Of course, you can have multiple links. There's a lot of tricks you can play, but this is a potential bottleneck of performance. Regardless of even if you have 100 gigabytes per second worth of SSDs plugged into this thing, your performance is going to be bottlenecked by the network. So there's that. Yes, and that connects to the single node performance limitations. You can have performance limitations of the CPU, of the memory on the NAS box, network performance, things like that. So there's a trade-off being made between manageability and performance and all that stuff when you go with this direction. Another direction is the topic of storage area networks. In the beginning of the world, beginning of storage area networks, or SAN, SANs used to mean a separate network just for storage traffic, separate infrastructure of switches, cables, and all that stuff just to connect the storage devices together. Things like fiber channel, etc. It's not as popular as it once were, but it was first created for the purpose of using SANs because generic Ethernet that was available at the time was too slow to function as a storage area network. It includes, switches, hubs, and the usual infrastructure. It's just there's another one of these separate from the regular Ethernet infrastructure used exclusively for storage area networks. It is easier to scale because it is managed by adding just more storage, plugging more storage into the wall to connect it to the Ethernet, connected to the SAN ports. And performance is distributed across multiple storage devices. So you can get pretty good scalability, you can get pretty good performance. So that's used to be a very important, popular way to get network storage. And you can typically SANs don't, unlike NAS devices, they don't expose a file system abstraction. They expose a block level access, so page level access into the storage devices in the network, to the individual storage devices in the network. A controversial opinion may be that traditional separate SANs are kind of dying out because Ethernet has become so fast with 40 gigabit Ethernet, 100 gigabit Ethernet. Ethernet is pretty much unifying all networks in the data center. Yeah, 10 gigabit Ethernet, 40 gigabit Ethernet, slowly subsuming fiber channel, even InfiniBand, although InfiniBand is very much going strong, but they are working towards just unifying all the networks in the data center over Ethernet. So traditional separate SANs might not be as deployed as much as before because even the storage devices plug directly into the Ethernet, but the idea is still there. Storage devices plug into the Ethernet and you use the Ethernet network infrastructure to communicate with remote storage, which is what storage area networks is. Another dimension of working with storage is the converged infrastructure. And this is not just for storage. It also works for network accelerators, memory, things like that. In a converged infrastructure, you can have a computation, memory, storage, all the, like a regular old desktop. All these things can be converged into a single unit. You can have a single box with some amount of computation, some amount of memory, some amount of storage, and then you just replicate the same thing over and over and over again. this can be easy to manage compared to having separate storage domains. And the reason this statement seems to conflict with what I was talking about when I was talking about NAS is that software became better because of distributed file systems like ZFS or HDFS or whatever, which can actually collect all the storage devices that exist on separate servers, even if they're local attached, and then expose a more or less single logical volume. And software for actually distributing work to where the storage and data is has also become better with with technologies like MapReduce and etc. And given the software, better software, it does also represent a little bit of decreased complexity. When a node dies, you don't have to worry about what to replace. You just simply replace the whole thing. And although this approach still does suffer from a little bit of the downsides that I was talking about, the manageability of NAS, for example, if you want to scale the storage capacity by 1.5x, do you just only upgrade half of the machines, for example? All of that issue is still there. But it has become cost-effective. Converged infrastructure has become a cost-effective way of doing things because of the economy of scale and the cost-effectiveness of commercial off-the-shelf parts, namely PC components. Because of the economy of scale, there's so many of these things being manufactured around the world. The cost point per performance, cost point per capacity of these commodity devices have become so low. Just having stamping the same thing out multiple times has become the more cost-effective way of doing things. And one of the new and novel and leading technologies of Google when they first came around was actually this. Instead of building, and here's a title of a blog post which you might find interesting. I might actually link this to the course website as well. When they first came around, instead of the traditional way of building large cluster system, large supercomputers, things like that, the Google infrastructure was kind of famous for just installing thousands and thousands of regular old PCs and writing good software that just makes management and performance distribution across these regular old PCs better. And the numbers probably have changed quite a lot, but since when I first heard these numbers, but when I was hearing about Google's scale of their commodity PC data centers, someone has mentioned to me that Google at that point in time was the third largest PC manufacturer in the world. But no one, of course, now you can buy things like Chromecast or Chromebooks or whatnot. But at the time, there was no, say, Google branded PCs available. They were the third largest manufacturers of PCs in the world, and they were using all of them inside their data centers. So that was the scale that they were talking about. And yes, another, if you go further down that dimension, there's the issue of hyper-converged infrastructure. In the hyper-converged world, it is still a relatively homogeneous units of compute memory storage. So it's the same PC class machine stamped over and over thousands and millions of times. But in the hyper-converged infrastructure, compared to the converged infrastructure, where each of the software running on say, a Hadoop cluster node running on a converged node could see its own CPU, could see its own memory, could see its own storage device. It just exposed a higher level programming abstraction to the outside world. In the hyperconverged infrastructure, there is a middleware layer which virtualizes each resource unit. It virtualizes the storage, it virtualizes computation, it virtualizes memory, so that the software running on a hyperconverged infrastructure can pretty much act like requesting virtual machines. It can ask for a certain amount of memory, it can ask for a certain amount of computation, it can ask for a certain amount of storage or bandwidth. And each unit can be scaled independently because the performance distribution, the access management, all that stuff is managed by the middleware layer. And there's good examples like this, including the VMware vSAN is supposed to be very helpful in doing a good balancing between taking advantage of the economy of scale when you buy off-the-shelf parts, and then better management via elastic allocation of resources. Right, yeah. A cloud VM can be configured to access an arbitrary amount of virtual storage and things like that. Okay, so we have run beyond time. So we have issues like computational storage, which I would have really loved to talk about, but it seems that we don't have time for this. Maybe I'll upload the slides to the course website. If you can take a look through them if you're interested. And if you want to further talk about it, we can set up a time as well. This computational storage stuff is actually one of my most biggest research topics of interest for me. So I would really love to have talked about it, but oh well, alas.